Okay, in the last video, we derived the formula for the Laplace transform of e to the at times a function whose Laplace transform we knew. And we said we're mostly going to care about the times when that function that we know is sine omega t or cosine omega t, so we actually wrote out the specific Laplace transforms we got for e to the at times those trig functions. Those are actually two of the formulas 3 and 8, that are given on your formula sheet. For both of those, we have the restriction that s has to be bigger than a, and I will again just caution you, use the formula sheet, don't use the table that's found in your book. The table that's found in your book gives correct formulas, but it's got some missing information. There are several formulas where they leave off the restriction on a that we need to have, and these are two of those. Okay. All right. When we get to the point where we're actually using this stuff to solve differential equations, which you would think we would want to do, this being a course in differential equations, one of the steps we're going to have to take is to find the inverse Laplace transforms of things that maybe look like this. And that can be a little bit tricky, so I wanted to just spend a little bit of time just focusing on that. Okay, so I've got two problems up here. What I want to do is work through this one together. Then I'm going to suggest that you pause the video and try this one on your own, and then come back and we'll work through it together. Okay. All right. So I've got this lovely, proper, rational function here. So of course the first thing I'd look at is, can I just factor the denominator? And the answer is no, that does not factor. This is an irreducible quadratic. Okay. So if it's an irreducible quadratic, I'm not super crazy about having that because I can't break this up into linear factors. Okay. What I want to try to do is make it so that the denominator looks like the denominators that I have here. I'm thinking I'm eventually going to make it match something that looks like this because I've got just a number on the top here. Whereas I'm thinking this one, where I have an s on the top, I'm going to make look something like this because I have an s on the top there. Okay, but I want to make the bottom look like s plus or minus some number squared plus some other number squared, because then I have some hope of matching one of these formulas. So the way I'm going to do that is by completing the square. So looking at just the denominator there, I've got s squared plus 4s plus 13. Now I'm purposely leaving some space here because what I want to do is say, if this were a perfect square, so if this were s plus some number squared, and I usually think of it in terms of s plus some number squared, and then I recognize that in this formula I'm viewing it as s minus a number squared. Okay, but what I would do is take that 4, divide it by 2, so I would get 2, square that, and that would be 4, so I'm going to add 4 and then subtract 4. That way, I'm just adding 0, okay? But now, these pieces are s plus 2 quantity squared, okay? And then this is just plus 9. So I'm able to rewrite that denominator as s plus 2 squared plus 9, so that it's going to look like this. It's just that my a here would be negative 2. Because if I'm adding 2, I'm subtracting a negative 2. Remember, the reason that that works is because s plus 2 squared is just s plus 2 times s plus 2. So I would get s squared plus 2 copies of 2s plus 4. Okay? So the reason we cut this 4 in half is because I wanted to say that was 2 copies of this number times s. I needed to know what that number was, and then whatever that number is, that's the number that I square to get the third term in this trinomial here. Okay, so I can now rewrite things that way. So I can say 1 over s squared plus 4s plus 13 is 1 over s plus 2 squared plus 9. Okay, so I'm kind of liking that. Just looking at the denominator here, So using formula 3, my a would equal -2. This has to be omega squared, so my omega would be 3. Usually we choose omega to be a positive number because we can, and that's simpler. If I wanted to make it -3, I could, but I just need a number that squares to give me 9, and 3 is going to be simpler. So if I take a look, I want to have a 3 on top. I don't have a 3 on top. I have a 1 on top. So I'm going to multiply by 1 in the form of 3/3, and I'm going to get 1/3 of 3 over s plus 2 squared plus 9. Okay. So now I can say the inverse Laplace transform of 1 over s squared plus 4s plus 13 is the inverse Laplace transform of 1/3 of 3 over s plus 2 squared plus 9. But that's going to be 1/3, just pull that scalar through, and then we said this matches formula 3 with a equaling -2 and omega equaling 3, which means when I apply the inverse Laplace transform, this is what I'm going to get. I'm going to get e to the -2t times sine of 3t. Excellent. So that's how that worked for this problem. Now, I want you folks to try it with this problem. See if you can take the inverse Laplace transform with this. Pause the video, work it out, come back, we'll work through it together and you can check your work, or if you got stuck, you can get unstuck. Welcome back. Okay. So, looking at this, I'm going to start with just the denominator. I've got s squared plus 2s plus 5. I probably want to first of all confirm that this does not factor, and it doesn't. If you're not sure, use the quadratic formula. If the quadratic formula gives you real roots, it factors, because then you would have s minus a root is a factor, and you can get all of your factors that way. Okay. If you get complex roots, it doesn't factor, and so you know it's irreducible. Okay. You can probably see by inspection that this one didn't work. Okay, so I'm going to say this is s squared plus 2s plus 5. Cut that in half to get 1. 1 squared is 1, so I'm going to add 1 and subtract 1. And that way this becomes s plus 1 squared plus 4. Okay. So I'm able to write that denominator as s plus 1 squared plus 4. Okay. I'm liking that. Okay. So if I take this whole fraction, let's see, I'll just remember that. S over s squared plus 2s plus 5 is s over s plus 1 squared plus 4. That's an s. Okay, so with there being an s on top, I'm thinking I'm trying to match this formula, but it's a little tricky because I don't have an s minus a on top. So let's figure out what is our a. So if I were using either formula 3 or formula 8, my a is the number I'm subtracting from s, so that would be -1. My omega is a number that squares to give me 4. I'm going to pick the easier one. I'm going to pick 2. Okay. So the denominator matches with that choice, but what I want to have on top is s minus -1. I want to have an s minus a on top. I want to have an s plus 1. Whenever I'm squaring here, that's what I want on top. Oh my goodness. So I'm going to add 0. So in math, we multiply by 1 all the time because that changes the way things look without changing their value. Well, here, all I did was added 0. That changes the way it looks without changing the value. But now, oh, this is so exciting, I can say that's s plus 1 over s plus 1 squared plus 4 minus 1 over s plus 1 squared plus 4. I can distribute the division, but instead of distributing it to all three terms on top, I grouped it so that I get an s plus 1 on top. I'm liking it. This now matches formula 8 with my choice of a being -1 and omega being 2. This is so exciting. This now has just a number on top. So I want to try to make this match formula 3. But that means that the number that I want on top is 2. So let's multiply by 1 in the form of 2 over 2. So if anybody asks you, what are you learning in differential equations? You are learning to multiply by 1 and to add 0. These are incredibly important skills. Okay, so I'm liking this. Now we should be able to take the inverse Laplace transform of this, because now I'm taking the inverse Laplace transform of s plus 1 over s plus 1 squared plus 4 minus 1/2 of 2 over s plus 1 squared plus 4. And we had said our a was -1 and our omega was 2, and that's what I'm using in both formulas 3 and 8. So here I'm using formula 8, so I'm going to be getting e to the at, so that's e to the negative t, times cosine omega t, so times cosine of 2t, minus 1/2. Now I can take the inverse Laplace transform here, which matched this formula, so I'm going to get e to the at, so that's e to the negative t, times sine omega t, plugging in my 2 for omega. So there's a lot of algebra we've got to do in order to make things match, in order to be able to take that inverse Laplace transform.